6.1 is about another way that we combine functions called composition. If I have two functions, f and g, then f of g, that little circle there is red, of f of g of x is defined to be f of g of x. That is, this function is created from f and g by first taking x. The way it works, it first takes x, plugs it into g, and whatever the output is, it takes that output and plugs it into the machine f. And the final output of this function is whatever f does to that. Let's look at an example. Let's suppose f of x was x over 3 minus x, and g of x is 2x over x plus 1. Let's ask ourselves, what is f of g of x? So that's f of g of x. G of x is exactly what's written there. So this is f of 2x over x plus 1. But what's f of that? Here's f of x. F of something more complicated is gotten by replacing the x with this more complicated thing. Here's a tip that works. Try writing the function just with a set of parentheses. F of x is this, so f of whatever I put there is going to be that thing, 3 minus that thing. It's like I replace the x with an open set of parentheses. Now put in the 2x over x plus 1 everywhere where you put yourself those parentheses. There, that's f of g of x. I'd like to simplify that. I notice it's got little fractions within the big one, so to make all of them go away, I'm just going to multiply top and bottom by x plus 1. And when I do, when this hits that, the x plus 1s will cancel, and in the numerator there's just going to be a 2x. When this hits that, I have to distribute it across this sum. I multiply by the 3. Great. When it hits that, I'll just have a 2x again. I think I can make this fit in here. It's 2x over, let's see, down here there's going to be 3x plus 3 minus 2x. That's just going to be x plus 3, isn't it? Here's an interesting thing. What's the domain of f of g? Well, you'd be tempted to look at that and go, well, we've simplified it. The domain, that's pretty easy. There's only one denominator. There's no radicals. The domain is all x's except negative 3, because negative 3 is the only thing that causes a 0 in that denominator. But look back at the original thing before we simplified it, right there. There's some little fractions within the big one. They also have a denominator. The denominator is x plus 1. It must be that x plus 1 can't be 0 either. If it were, this wouldn't have existed. So something was lost. The information that x is not allowed to be negative 1 was lost when we did that simplification. I mean, I'm all for doing simplification, but the interesting thing is that the fact that the original function prohibits x equaling negative 1 disappears when I do that simplification. Something in the simplification assumed that x wasn't negative 1. In fact, it's right here. When I multiply by x plus 1 over x plus 1, you can't multiply by 0 over 0. That's not equal to 1. So this simplification inherently carried with it the assumption that x plus 1 wasn't 0. So if I want to find the domain of f of g, it's best to look back at the unsimplified version so I don't miss anything. So I see little fractions and a big one. The little fractions tell me that I need x plus 1 to be not 0. And the big fraction tells me I need 3 minus 2x over x plus 1 to be not 0. Okay, I just need to solve these guys and find out what x's I have to exclude from the domain. Well, the solution to that is x equals negative 1, so x is not allowed to be negative 1. Well, what's the solution to that? So 3 minus 2x over x plus 1 equals 0. This is an equation, so it's safe to multiply both sides by x plus 1. I'm running out of room though, so it's not safe for me to write down below here. So I'll multiply by x plus 1, and I'll get 3 times x plus 1 minus 2x equals 0. Boy, that looks familiar. Oh, that's that thing that we just did. That's x plus 3. So if I want this to be non-zero, then I better have x plus 3 not equal to 0. That is, x can't equal negative 3. That means the domain, I think I can just squeeze it in here. The domain is all numbers except negative 1 and negative 3. That's a reasonable answer considering how much space I've got left. I'm not going to bother putting that in interval notation. For this example, let's use the same f and g, but now let's find g of f of x and its domain. So g of f, that's g of f of x. So f of x, that's literally what's right there. Right, look at the symbols exactly the same as that. So that's x over 3 minus x. But g of this thing is it's what I get when I replace the x's with this more complicated guy. So I'm going to try to write g. Instead of with x's, I'll just write it with big open parentheses to include something that will go in. So g is 2x over x plus 1. So 2 parentheses, set of parentheses plus 1. That's g. And inside these, I put the x over 3 minus x. There's g. And I'd like to simplify it while I'm right here. The top will be 2x. The bottom will be x plus 3 minus x, isn't it? X plus 3 minus x. Oh, look, the x's cancel. It's just 2x over 3, or 2/3 x. If you looked at this guy and said, what's its domain? You'd say, what's the whole real numbers? It's defined everywhere. But in fact, we should look at the unsimplified version to learn what the domain is, because steps that we took during the simplification might cause certain points in the domain to disappear, to sort of fall out of sight. So there are little fractions who can't have a zero denominator, and there's a big fraction whose denominator has to be non-zero. So the little fraction's denominator says we need 3 minus x to be non-zero. And the big fraction says I need this to be non-zero. So let's solve. Where does this equal 0? Well, that's at x equals 3. So I can't have x equal 3. Let's try to solve this guy. Let's multiply both sides by 3 minus x. I did that earlier. And I got x plus 3 minus x. I want to know, where does that equal 0? Well, the x's cancel on this equation. If I set this equal to 0, it turns out that 3 equals 0. That has no solutions. That is x over 3 minus x plus 1 is never equal to 0. So the only condition placed on the domain is by the little fraction. The domain is all real numbers except x equal 3. Let's try one more. For this f and that g, let's find f of g of x. So let's see, f of g of x is f of g is this thing 1 plus 2x over x minus 1. I wish I'd left myself more room. I'm going to write f with parentheses. F of whatever you give me is that thing plus 1 divided by that thing minus 2. So f, if I have a 1 plus 2x over x minus 1 here, equals this stuff with all these parentheses guys equaling 1 plus 2x over x minus 1. Let's not bother finding the domain. It's good exercise, but let's not find the domain. Let's just simplify it. I'd like to clear out the little fractions within the big one. I'll multiply top and bottom by x minus 1. That's 1. So when I distribute it across the sum in the top, I get 1 plus 2x when this hits that fraction. It also hits this 1, so plus x minus 1. I have to distribute across the difference in the difference in the bottom, so when this hits that, the x minus 1's cancel and I'm left with 1 plus 2x. But then it hits this and I'm left with minus 2 times x minus 1. Let's see. Top is 1 plus 3x minus 1. The top is 3x. What's the bottom? This is 1 plus 2x minus 2x plus 2. So the bottom is 3. Well, that's interesting. It's x. Let's try something else. What is g of f of x? So that's g of f of x. G does this to its input. 1 plus 2 times its input divided by input minus 1. I'm just looking at g and replacing the x's with just open parentheses to, collect the input. And the input is this. It's x plus 1 over x minus 2. Let's find the domain some other day. How would you simplify this thing? You could get rid of all the little fractions by multiplying top and bottom of the big fraction by x minus 2. Now let's do that and see what we get. So distribute. When this hits the 1, of course I get x minus 2. When it hits that, the x minus 2's cancel. I'm left with 2 times x plus 1. In the bottom, when this hits that, the x minus 2's cancel, and I'm left with x plus 1. But then it also hits the minus 1, so minus x minus 2. Let's get rid of the parentheses and collect up like terms. So x minus 2 plus 2x plus 2 in the top. In the bottom, x plus 1 minus x plus 2. In the top, it's 3x. In the bottom, it's 3 again. So it's x again. That's interesting, because we saw in the first example that if you compose two functions in different orders, you get different things, possibly. So here it's kind of remarkable that f of g and g of f are the same thing. In fact, there's something really simple. They're just x.